The last session is about offloading. The first talk is about offloading packet processing to SmartNICs. And our presenter is Jiarong Xing. He's a final year PhD student in Rice University. He's been interested in building high-performance and secure networks using programmable accelerators. He's on the job market for faculty jobs and industry positions. Please do talk to him afterwards. Jiarong, please.
Hi, thanks for the kind introduction. Today, I'd like to talk about how to unleash the potential of SmartNICs to deliver high-speed packet processing when you program them in P4. This is a joint work between Rice, NVIDIA, and UW. SmartNICs are increasingly deployed in today's data centers with many networking functions offloaded onto them. This not only improves the networking performance, but also saves CPU cycles. Different types of SmartNICs are available on the market, and in our work, we primarily focusing on one major type of them, multi-core-based SmartNICs. One example is the NVIDIA Bluefield SmartNICs, which are also known as DPUs. Bluefield is equipped with a set of ASIC cores for high-speed traffic processing, and they also have a bunch of ARM CPU cores for more flexible operations. Recently, P4 is emerging as a unified programming language for SmartNICs and has been adopted by many SmartNIC vendors, such as AMD, Pensando, or Netronom. And NVIDIA is also developing the P4 interfaces to program their Bluefield ASIC cores. Multi-core SmartNICs are flexible, and they have the potential to deliver high performance, but they do not have a strong performance guarantee. And this is different from stage-based programmable switches as shown on the left that can always run at line rate if the P4 program can fit into the pipeline. Multi-core SmartNICs process the packets in a run-to-completion manner as shown on the right. It has a high variability in performance depending on the traffic workload and the program implementations. So for a given workload, inefficient implementations could lead to low performance. Therefore, performance optimization is very critical to achieve good performance for these multi-core-based SmartNICs. But unfortunately, today's P4 compilers are mostly designed for the stage-based pipeline processing, so they're mostly focusing on optimizing the resource usage rather than the performance. So we need a better P4 compiler with performance optimization support for these new types of SmartNICs. But this is not an easy job because multi-core SmartNIC performance could vary based on runtime profiles such as traffic distribution, flow length, table entries, and others. For example, different traffic distributions could lead to different bottlenecks in the program, which makes it hard to determine which part of the program we should focus on, we should optimize. And even if we find an optimization, there's no guarantee that it can always work well. For instance, the flow cache optimization can work well for long flow dominated traffic, but it could have less or even negative performance gain when the traffic shifts to mostly short flows. Because in this case, most packets will miss the flow cache and go to the slow path. These profiles are unpredictable during compilation, and it can dynamically change as the system runs. Because of this, the compile time optimization is very difficult to produce desired performance improvement. So to solve this problem, we believe the SmartNIC pipeline should have the ability to adjust its implementation to match the runtime profiles, just like a chameleon that can change its color to match the surroundings. To this end, we build a pipeline in this work, a runtime profile guided optimization framework for multi-core SmartNICs. Here is the workflow. Pipeline provides a profiler that can constantly monitor the SmartNIC pipeline and collects runtime profiles. These profiles will be fed into the optimizer, which compute the optimization accordingly and generate an optimized P4 program. And we will replace the P4 program running on the pipeline with this optimized version. And these cycles can be triggered periodically or in response to the profile changes. So as you can see, our system requires to upgrade the P4 pipeline at runtime. And this is enabled by our prior work, FlexCore, which is presented at the NCDI 2022 and also Hardships this year. FlexCore enables us to upgrade the P4 pipeline in place at runtime without any downtime. And we use this capability to build this runtime optimization framework in this work. The key research question we need to address is how and where to optimize SmartNIC P4 programs. In terms of how, we develop a set of performance optimization techniques. Let's look at the two examples. The first one is table caching, which allows us to skip complicated table matches using the cached result. And the other one is table merging, which can merge multiple smaller tables into a big one so that we can perform them together and save memory accesses. Pipeline customize these techniques for multi-core SmartNICs. For instance, traditional flow cache usually use only one cache for the entire program, which tends to have the cache entry cross-product problem and thus having a low cache hit rate. But pipeline supports a more flexible caching strategy, where we can use multiple and smaller caches to avoid this problem. Our system will automatically decide how many caches we need and what tables we need to cache. For table merging, we take the table types into consideration, but I won't dive into the details. You can refer our papers to see more discussion and more optimizations. Different optimizations will generate different performance gain, and at the same time, they incur resource overhead. So our next research question is how to maximize the performance gain within the resource constraints. If we naively search over the whole program exhaustively, it will generate a huge search space, because each table can take a different optimization, and we also need to consider all the combinations across all the tables in the P4 program. Our insight to solve this problem is that code pieces do not contribute to the processing latency equally. Some code pieces are the main bottleneck, so we could prioritize optimizing them, which tend to unleash more performance benefits. Concretely, we partition the P4 program into what we call pipelets, and each pipelet is a straight-line P4 code. Then we use our runtime profiler and our custom model to compute the processing latency for each pipelet. And this way, we can select the top key pipelets, which contribute to the most processing latency. And then we use a searching algorithm to compute the best strategy for these selected top key pipelets. We evaluate our framework on both NVIDIA BlueField-2 SmartNICs and the Zhuolong SmartNICs. Here are some highlights of our results. Our benchmark demonstrates that our optimization techniques have significant performance improvement. For instance, table merging can improve the throughput by up to 2.1 times on both SmartNICs. And our end-to-end case study demonstrates that our system can capture the profile changes at runtime very quickly and re-optimize the pipeline to improve performance. And finally, our top key pipelet-based search is also very effective. For instance, when key is 20%, we can already achieve more than 70% of performance gain found by exhaustive search, while reducing the search time by up to 8.2 times. In summary, today's P4 compiler lacks performance optimization needed by multi-core SmartNICs. And we build pipeline in this work, an automated performance optimization framework. We have a set of P4 performance optimization techniques, and our system can adapt to profile changes at runtime very quickly. Runtime programmability is in great demand, and our community has been doing a lot of work, including the best paper this year, which is also related to this direction. Now here is a profile of our work on the runtime programmability direction with a different take. You can find more details on my personal webpage. With that, I'd like to conclude my talk. Thank you.
Hello, nice talk. I'm Daehyuk from UT Austin. It's a great, very interesting work. So my question is, in the earlier talk, you're kind of assuming this programmable the SmartNIC has the runtime reconfigurability, and also it's based on multi-core architecture. But in the evaluation, you use like existing Bluefield and the Metronome NICs, which do not support such a capability. So how did you evaluate your system under these existing platforms?
Right. So our system do not always require this runtime programmability, but if your SmartNIC have such ability, it's great. Like you can directly use that to do this runtime optimization, like the NVIDIA Bluefield SmartNICs. But there's another trend recently led by Microsoft, which is that the SmartNICs are deployed in a disaggregated manner, where you unplug the SmartNIC from the servers and you put them into a dedicated chassis with a lot of SmartNICs that provide services for a rack of servers. So in that case, you can perform runtime optimization, like upgrading the P4 pipeline by draining the traffic to a neighboring NIC temporarily, and then you load the new program, you entering the traffic back. You can still achieve runtime upgrade of your pipeline. So we work both for this, our system works for both cases. And for Metronome, we assume you can do this, you can utilize this disaggregated architecture, and you can join the traffic to the neighboring NICs for upgrading.
Hi, this is Jiarong from UT Austin. Thank you for the talk. I have a very quick question. Like you mentioned in the earlier slides, like you are using SIGCOMM' and you are assuming the run to completion execution model. But there is some existing work that they are using the same SIGCOMM' but not relying on the run to completion model. For example, they split the pipeline into different cores and multiple cores run in a pipeline manner. So I'm wondering how much optimizations you proposed in your paper is tied with this run to completion execution model, and like, is there any other optimization not tied to this? Yeah.
Yeah. So to clarify, are you talking about like SmartNICs having a P4 pipeline using the stage-based architecture? Yeah, so as I mentioned, there are different types of SmartNICs available on the market, and there's one type of them is that the P4 pipeline still adopt this stage-based architecture, which is very similar to programmable switches. In that case, mostly the performance is deterministic. Like I said, if you load the P4 program to the pipeline, you achieve good performance. But for multi-core SmartNIC, we have this performance variability. That's why we focus on these types of SmartNIC. But even for this stage-based pipeline, there is still a possibility, as you mentioned, like your program cannot fit into the P4 pipeline, and you have to partition them. So we have one specific technique that allows you to partition the pipeline into these two parts, and we take care of the migration overhead. Like we have optimization to minimize such overhead. You can find more details in our paper.
Okay, we will leave the rest of the questions to the panel's time. Thank you for speaker. So our next talk is about programmable switches, offloading to programmable switches. When we're offloading many applications, there's a memory management question. So the project is ActiveRMT. It's actually the best paper of our conference. So let's welcome Rajdeep. He's from UCSD. He's a PhD student from UCSD. He's graduating next year. And he's been working on programmable switches for various function offloading and revisiting the approaches from active networking. So, Rajdeep, go on.
Hello everyone. I'm Rajdeep. I'm a PhD student at UC San Diego. And I'll be talking about how to perform memory management in ActiveRMT. So I'm sure a lot of you are aware of the RMT-based programmable switches, which is also commercially known as Tofino. And these devices allow you to run application-specific functions on the network using a tool chain, for instance, P4. But the problem is that you can run only one program at a time on these RMT pipelines. So on a shared device, if you wanted to run multiple programs, you would have to combine them into one. And this is not only a tedious task, not to mention error-prone. We also do not know of any approach that is able to automate such a thing for arbitrary programs. To make things worse, the process of updating the RMT pipelines is not hitless, and it results in network disruption when you reset the switch. So these devices are not are a bit limited in their ability to perform runtime allocation. So we came up with ActiveRMT that enables each packet to carry a distinct program which can then be run on switches using capsules. In order to enable sharing, there's also a controller that monitors and manages switch resources. Of course, security is a concern that everyone has. So we also assume a network where packets can be authenticated at source, for example, using access control lists. Now, in order to avail in network computation, individual users can write applications that insert active programs into network packets. And these active programs are constructed using instructions derived from the Tofino native architecture. The activation process itself is pretty straightforward for stateless applications. All that the client has to do is simply encode the active program into network packets before sending it out on the wire. For stateful applications, however, you need an allocation, memory allocation. So this comprises of 3 phases. So in the first phase, the application client requests an allocation, and the controller accordingly responds with an allocation based on the available switch resources. The client then uses this allocation to synthesize an active program, which it then encodes as packet headers. So in this way, instead of having to deal with combining multiple programs and running them on a shared device, we now have one P4 program that runs multiple active programs. We call this the switch runtime. So to enable this, we statically allocate a set of match action stages in RMT to run the active programs, where each active stage runs one instruction. Now, RMT stages are all identical, which means that we can run any instruction on any stage. Also, the packets can be recirculated on current devices, so programs that are longer than the number of instructions, the number of stages can recirculate and run to completion. This, of course, costs additional bandwidth. But the most coveted resource on programmable switches is actually memory. And what this means for a shared device is that stateful applications would have to reserve memory to avail functionality. So that brings me to the crux of this talk, which is how to perform memory management in ActiveRMT. So when allocating memory, we use a memory layout that consists of a 2-dimensional array of memory blocks, where each block has multiple 32-bit memory objects. Virtual addressing is expensive on current devices such as Tofino, and so we use physical addressing instead. And we enforce memory protection, and for memory protection, we perform isolation using TCAMs, which also allows us to achieve more fine-grained memory partitioning. To make a better memory allocation decision, we identify applications as one of 2 types based on their utility characteristics. So we refer to applications as inelastic if they have a fixed demand, and elastic if they have variable demand and their utility increases with more memory. So an example of such an elastic application would be an in-network cache, and a corresponding program that simply queries the switch for a cached object is shown here. So this program has 3 memory accesses, one corresponding to each memory read instruction. The program simply reads an 8-byte key and a 4-byte value from the switch cache, and if there's a hit, it sends that a cached object back to the sender. So this program requires 3 memory stages. When attempting to allocate such an application, the controller can simply allocate all the memory blocks corresponding to those 3 stages to this application. Let's say another instance of this application arrives. Since these applications are both elastic, the controller can simply split the same set of stages between the 2 applications. However, note that the first application has to yield some of its memory, and this results in a disruption to application functionality. We refer to this as the reallocation cost. Now, fortunately, there's a way to avoid this. Since memory is fungible and the runtime is functionally redundant, we can run any instruction on any stage. So in this case, for the second cache instance, we can simply push the instructions down so that the memory read instructions of the second application does not conflict with the first one. We call this mutating the active program, and the corresponding program as a mutant. The controller takes advantage of mutants. The controller takes advantage of mutants when making an allocation decision. And these mutants are synthesized by the client upon receiving an allocation. So not only do mutants allow us to completely deconflict, as we see over here, it also improves utilization by allocating more memory overall to the applications. So to see how this works in practice, let's consider a scenario where we have 4 instances of such a cache application that arrives one after another, separated by a time of 5 seconds. To keep things simple, we populate each of these cache instances upon allocation. We also choose a workload that allows us to achieve a maximum hit rate of around 85%. So the first application arrives at time t equals to 0. Now, the time it takes to deploy this application is approximately 100 milliseconds, and this includes the time to coordinate with the switch, the time to compute the allocation, update the tables, and so on. When a second application arrives at time t equals to 5 seconds, know that the controller is able to hitlessly provision that application. And it is able to do so because it is able to find a mutant that does not conflict with the first application. This is true even when a third application arrives and the controller is able to find an allocation that does not conflict with any of the previous 2 applications. However, when a fourth application arrives, the controller is not able to find a mutually exclusive set of stages for this application. And so it decides to share the memory region of the fourth application with the first application. This, of course, requires the first application to yield some of its memory and results in a brief disruption of around 100 milliseconds. Even then, the total allocation time is just a few 100 milliseconds for the fourth application. Note that the second and third applications are still unaffected. So in practice, we can have a lot more applications, let's say hundreds of applications. So we simulate an increasing population of 3 types of applications following a Poisson distribution, where in expectation 2 applications arrive and 1 departs. So we take a look at 2 types of allocation modes. The default one, which is called most constrained, is the one where the controller does not allow application traffic to consume any more bandwidth that was originally necessary. In the other type of allocation mode, which is least constrained, the controller does consider recirculations to find a better allocation. And as you can see over here, such a strategy does allow the system to achieve almost 100% utilization initially. However, the gains diminish over time as memory starts fragmenting, and both these schemes stabilize to around 75%. So in summary, we present a system that allows rapid, non-disruptive provisioning of user-defined applications on programmable switches. And our approach does not require operator intervention for reprovisioning the switch for, say, a combination of services. And we are able to do so using a capsule-based approach to active networking and a mutant-based allocation approach that not only helps improve the degree of multi-tenancy, but also memory utilization. One of the shortcomings of our approach is that certain types of applications, such as firewalls, cannot be implemented because of the trust model. But the good news is that we do plan to address that as a part of our future work. And with that, I will end the talk. Thank you for listening.
Questions?
Hi, Darius Grassi from UT Austin. So this design is specifically for the Tofino architecture and built inside of the RMT architecture, but we've seen a plethora of other programmable devices, both for programmable switches and SmartNIC. So how well do you feel this design philosophy for running multiple applications at runtime can be ported to other programmable devices in the future?
Thanks for the question. The current design does assume an RMT architecture, but more specifically something that's similar to TNA or the portable switch architecture. So the basic idea is to have a run to completion model for those devices where you can deterministically run programs once you write them. So in future, if any of the current devices can be exported as a TNA or a portable switch architecture, the current approach can be carried forward to those devices.
Hi, Nate Foster from Cornell. Really cool work.
Thank you.
I was curious how you handle updates to registers. So Tofino has these stateful ALUs, and you usually have to provide the read, update, write sort of procedure as a fixed block. It's not clear to me how you would do that in a capsule and have a base program that could interpret, a large range of possible stateful ALU operations.
Thank you. That's a great question. So, indeed, if you want to, you cannot. The Tofino register ALUs do allow for complex arithmetic logic operations on the register ALUs, and so we choose a set of such operations as a part of our instructions. And that includes read, writes, and increments, which are some of the most commonly used primitives. But then if a certain register requires revisiting to perform a read, modify, write, update for more complex operations, the current design does allow recirculation, which allows you to revisit the same register and continue execution of the operation.
Thank you.
Okay, we'll leave the rest question to panel time. So our next speaker is Xinyi. Next speaker is Xinyi Chen. She's from UPenn, fifth year's PhD student. She will present us the Cowbird project, which will be focusing on offloading memory disaggregation. And Xinyi has been recently working on building better systems for cloud applications that leverage new hardware trends and programmable network devices. Xinyi, please start.
Hi, thank you for the introduction. Hi, everyone. I'm Xinyi from the University of Pennsylvania. So I will introduce our work, Cowbird. Cowbird is a system which can free CPUs to compute by offloading the disaggregation of memory. This work is done by me and my collaborators, Chen, Zhen, and Vincent. Recently, there has been a lot of interest in memory disaggregation, which is a technique that can allow applications expand their memory capacity by leveraging remote memory resources. There are many different types of memory disaggregation, and one particularly interesting type is this farm memory architecture. Imagine there is an application running in a compute node. It can access its local memory and local compute resources. In the meantime, it can also access the remote memory. This gives the application an illusion that it has a large memory pool, and the application can achieve good throughput even when the working sets get larger than local memory. The critical component that makes this type of architecture work is this high-speed communication channel connecting the compute and the memory nodes. Today, most common approach is using RDMA. RDMA is so attractive because it can bypass the kernel. In the case of one-sided RDMA, it can even bypass the CPU involvement in fetching remote memory. Which means, compared with the TCP, one big benefit of RDMA is that it can reduce the burden of local CPU usage. However, is RDMA really good enough? Surprisingly, we found that there is still CPU overhead even in one-sided RDMA. We did a CPU time measurement for one-sided RDMA read request. We first post a work queue entry into the work queue and then poll the completion queue to check whether the task has been finished. And we measure the CPU execution time for single post and poll operators. We can see that even single post or poll takes several hundred nanoseconds for CPU time. To see why this is the case, so we further break it down into more details. So we found that there are several subtasks in the poll and post, including locking, ringing the doorbell, etc. Each of them requires expensive instructions like spin lock or mfence to ensure the proper ordering of the queue. As a preview of our system, by offloading all these operators, our system Cowbird can reduce CPU calls of RDMA and free all these CPU cycles to applications. Since even calling one-sided RDMA has some overhead, so why not free the CPUs on the compute node just like a Cowbird? Based on this, the core idea of Cowbird is to offload the transfer of memory away from the compute node. The design goal here is to convert remote memory access into local memory access. Then the remote memory access will be served asynchronously by our offload engines. There's a slightly trade-off here. The trade-off is that, so for the async stuff, it will introduce slightly more latency, but it brings the benefit of reducing CPU overhead and improving the throughput. The primary challenge in Cowbird design is the definition of an interface and a set of offloading protocols, which are general enough for all different kinds of offload engines, where some of them have very limited resources. In memory disaggregation, there are mainly two parts. One is the compute node, the other is the remote memory pool. In Cowbird, we add a third component. We call it offload engine. Cowbird is a very general framework to all kinds of offload engine, as long as the hardware can generate network packets and have some very basic computation power to process the packets. The hardware used as an offload engine can be a programmable switch, a SmartNIC, or spot CPU cores. Currently, we implement it with P4 switch and spots, but it can also be implemented on other hardwares like FPGA or SmartNICs. From the application's view, every time it wants to access remote memory, it only needs to do a local memory access to insert a request into a request buffer. After request is finished, it can do another local memory access to read the response from the response buffer. From the offload engine's view, it will issue RDMA read to read the application's requests from the compute node buffer, then processes to get information about remote access requests. Then it will issue some RDMA read or write access to the buffer pool in the remote memory. Finally, it will write back the response to the application's response buffer. As an application, how to interact with Cowbird, just like very simple read and write and epoll, we try to provide very simple interface to use. Due to the time constraints, I will focus on async read as the example during this whole talk. The application will call the async read API to issue a remote read request. Then it will receive a request ID from this function. Then using this ID, it can call function poll to check whether the remote data has been fetched. We separate data into the actual data and the metadata. Metadata contains all the information from remote memory access, and we only remit necessary parts to make metadata size as small as possible. We create 3 local RDMA buffers to store the metadata and the actual data for both read and write requests. So when an async read API is called, the metadata is inserted into the request metadata buffer. When the request is completed by the offload engine, the actual data can be read from the response buffer. So now let us focus on the detailed offloading protocols. We have 4 phases in these protocols, and the first one is the setup phase, where we initialize the RDMA connections, register the buffer regions, and send all the configure information to the offload engines. Then in the probing phase, the offload engine will keep sending RDMA reads to read the Cowbird request from an application's buffer. So step 1 is the offload engine will generate RDMA read to read the tail pointer of the metadata buffer. And in the second step, it will check whether there's update in the tail pointer. So for the third step, is there some update, which means there are new requests from the application, it will generate RDMA read to read the content in the request metadata buffer. And the fourth step is to parse the metadata from the payload. So after we parse the metadata of the application request, we know, for example, this is a read request, and the offload engine will fetch the requested data from the memory pool. So for the second step, after we get the data from remote memory, we will recycle the RDMA packet. So we convert the previous RDMA read response from step 1 into an RDMA write packet to write the data back. And then in the third step, because the SmartNIC will return RDMA ACK as the response of the previous RDMA packet in step 2, so we also recycle this packet and we convert it into an RDMA write to update the tail pointers of the response buffer. So in the evaluation section, we aim to address 2 key questions. Can Cowbird really deliver its promises of freeing CPUs on compute node? And with all these saved CPU resources, what benefits to applications experience? We did all our evaluations based on our 2 implementations, Cowbird P4 and Cowbird Spot. We use an open source key value store called Faster as our application. Recursive Faster is stored in a hybrid log, which is a log partitioned across main memory and storage. When the main memory is insufficient, all the data will be appended to the storage layer, which can be an SSD or remote memory. We adapt Faster through the iDevice, which is the interface for its larger than memory part of the log. Except for Cowbird, we have 3 baselines. The first is the default storage backend in Faster that uses a local SSD on the compute node. The second is the one-sided async and sync RDMA, where the storage layer is in the remote memory. The last one, we put the storage layer in a compute local memory, which represents the upper bound on disaggregating memory performance. We run Faster with YCSB benchmark, and we use the communication ratio to represent the CPU calls in memory disaggregation. So we can see that Faster with synchronous one-sided RDMA can spend more than 80% of its time on communication tasks, while asynchronous has much less CPU overhead compared with the synchronous one, and our Cowbird can further reduce the CPU cost and constantly spends less than 20% of CPU cost on communication. We further measure the throughput of and this is the performance. So we can see that Cowbird can achieve almost the same performance with the local memory, which is the upper bound. And this is the summary. Yeah, feel free to ask any questions.
Hello, this is Jiarong from UT Austin. I'm wondering, do you need the switch to constantly pull the host RDMA queue to get the request?
Yes.
So how, like the pooling will cause high PCIe and network overhead. How should you solve this problem?
Yeah, that's just a good question. So for the network part, we're using a low priority. So we put the probing packet into low priority. So we try to reduce the network overhead. And for the PCIe overhead, because the probing packet, we will only read a very small size of the data in the buffer pool, so the PCIe overhead is also low.
Yeah, but if the sending rate is high, it will still take a considerable amount of PCIe traffic. Yeah, but we can discuss it offline. Yeah.
Okay, thank you.
Yeah. Hello. Great talk. I'm Wei Gao Su from Purdue, right here.
Oh.
Yeah, so it's quite intuitive to offload read and write requests to the network. But as far as I know, RDMA also has other operation codes, for example, fetch and add and compare and swap. I wonder if does your design incorporate all that higher level operations into the system?
Thank you, it's a good question. So currently we're mainly targeting with the read and write because we think this is the most commonly used and especially in one-sided RDMA. But it can be in the future work for other operations.
Great. Let's thank the speaker.
Thank you.
So our last talk is Lumina. It's about offloading network stacks to hardware and understanding its behavior. And our speaker is Zhuolong Yu from Johns Hopkins University. He's recently graduated, and he's now in Microsoft Azure working on RDMAs. His interest is always in high-performance networking and programmable networks.
Thanks for the introduction. Last talk, finally. Hello, everyone. My name is Zhuolong Yu. Today, I will introduce Lumina, a tool we built to understand the micro-behaviors of hardware network stacks. It's a collaboration with Bowen, Wei, Shahar, Vova, and Xing. Hardware network stack is widely used. For example, in Azure, more than 70% of network traffic is RDMA traffic. In this talk, I will focus on RDMA. Here's a comparison of TCP/IP and RDMA. RDMA bypasses the kernel and implements its own network stack entirely in the NIC. It can achieve high throughput, low latency, and very low CPU overhead. To best utilize the performance, the network programmers should be familiar with the behaviors of hardware network stacks. While reading the specification is helpful, it may not cover enough details of actual implementation. For example, the specification may tell you how the go-back and retransmission works in general, but it normally will not tell you how the retransmission pipeline is organized in the hardware and how large should we expect the retransmission latency to be. It is more like a powerful black box to most of the users. The current practice to test the hardware network stack is to run end-to-end applications in test clusters. In this way, we can measure end-to-end performance and review functional bugs. However, there are 3 drawbacks. First, we cannot accurately capture the micro behaviors. Second, there are large noises brought by different network and application conditions. And thirdly, it has large resource consumption for some certain workloads. So what is missing here? We need a tool to enable developers to easily write precise and reproducible test cases. The tool should be able to interact with the network stack in a flexible and deterministic manner. And the tool should accurately capture the micro behaviors. Testing hardware network stack is challenging because of 2 reasons. First, as a network stack is kernel bypass and is implemented entirely in the hardware, we cannot inject packets or measure behaviors directly as an end host. Second, as a hardware network stack provides high performance, the testing tool should be able to interact with them at high speed and with very low actual latency. So we propose Lumina. Lumina uses a programmable switch as middle box to inject events to the traffic. Since the middle box may not have enough resource and flexibility to do the complex measurement, we mirror all the packets from the middle box to some servers for offline analyzation. Here we show the architecture of Lumina. We have 4 components: orchestrator, traffic generator, event injector, and a traffic dumper. To run a test, the orchestrator takes a configuration file as input and sends RPCs to each component to coordinate the executions. Our goal is to support users to write precise and reproducible test cases. The logic of traffic generator is quite simple. It has 2 roles, a requester and a responder. They will take the configuration, exchange the metadata, and then start the traffic. The event injector takes the user configuration as input. For example, the user can simply write a configuration saying, drop the second packet or the first QP. Then the user configuration is translated into data plane language. In this example, it is going to drop the packet with sequence number 1002 sent from the requester to the responder. And our event injector is required to identify each packet, including the same packet before and after retransmission. And you can check our paper for more details. Next, let's talk about the traffic dumping. We need to capture packets from both the requester and the responder. One choice is to use tools like IBDump or TCPDump to dump packets as an end host. However, it is unclear if dumping as an end host at high speed will impact the network behaviors. Besides, dumping packets at two servers may involve clock synchronization, which is also a hard thing to deal with. So in Lumina, we mirror the traffic to some servers, and the server will dump the traffic. When we do the mirroring, 3 actual fields are attached to the mirrored packets. Since we are using the mirrored trees to analyze the traffic, the first step is to ensure there's no packet loss in the mirrored trees. We use a mirror sequence number to ensure that. A legal trace should have consecutive mirror sequence number. And we use a field to store the event types that were injected to the traffic. And the timestamp field will support fine-grained time measurement. In this example, the requester sends 5 packets, and we drop the 3rd packet using our tool. So the responder only receives 4 packets, while other 5 packets are mirrored to the mirror server. The first packet will have sequence number 1, job tag 0, and the 3rd packet will have sequence number 3, job tag 1, meaning the 3rd packet in the original message was dropped. Upon finishing the experiment, the orchestrator collects all the results, checks the integrity, and do further analysis. The integrity check will make sure there's no packet loss in the mirrored trace, and the analysis can be customized by the users. Next, I will discuss our experiments and some findings. We tested 4 NICs from 2 vendors. In our testbed, we have 4 servers connected by a switch. 2 of the servers are traffic generators, and the other 2 are traffic dumpers. We have tested different network behaviors, such as retransmission, congestion control, and performance isolation. And we have found several bugs using Lumina. In this talk, I will discuss 2 of them. The first bug we found is called the noisy neighbor problem, which is on CS4 NIC. It means that when we have multiple flows running, packet loss of some flows can affect other victim flows. In the experiment, we established 36 connections. Each connection will do an RDMA read to fetch data from the remote side. And we pick I connections and drop 1 packet for each of the I connections. Ideally, only these I connections should be affected since they have packet loss. However, what we observed is that the victim flows are affected badly and have very large message completion time. Here's the result. The blue bars are victim flows. So when I is larger than 12, the victim flow's message completion time grows to hundreds of milliseconds, which is a disaster. By checking the NIC counters, we can find that there are many packets discarded by the NIC as a receiver side. When some tail packets are dropped by the NIC, timeout will happen, thus leading to this extremely high message completion time. And the second bug is that the ETS, or enhanced transmission selection, is not work conserving, meaning that the bandwidth is wasted in some cases. To trigger this bug, we can have 2 connections, and at the sender side, we map 2 QPs to 2 ETS queues, and we consistently mark ECNs for the first connection to simulate congestions. Ideally, the first connection should have lower throughput because of the DCQCN rate limiting, but the other connection should consume the spare bandwidth left. However, our experiment shows that the second connection didn't use the spare bandwidth, and the total throughput is much lower than what we expect. Here's an experiment result. In the first case, we map 2 connections to 2 different queues, and we don't inject any ECN. In the second case, we map 2 connections to 2 different queues, and we inject ECN for QP0. In the third case, we map 2 connections to a same queue, and we inject ECN for QP0. As we can see, in the second case, when we use 2 queues, and the throughput of the first connection is throttled, the other queue cannot use the spare bandwidth, and the total throughput is quite limited. So in conclusion, we need comprehensive tools to test and understand the micro behaviors of hardware network stacks. And we hope that Lumina can shed some light in this critical area. Thank you, and I'm happy to take any questions.
Thank you, very nice work. Tao Ji from UT Austin. So my question is this, mirroring the packets, you can have a packet trace of millions of packets. And is there any formal method or best practices that Lumina proposes for analyzing the behavior? Because a lot of times we don't know what is the anomaly that is caused by our use case. Can you share some of your experiences?
Yeah, sure. I didn't talk much in this talk, but in our paper, we have like another module that will guide us to generate some test cases that will help you find like potentially interesting behaviors, like higher retransmission latency or something. And also, one of the use cases is that, like for example, in Azure, when we got reported incident and we start investigating. For the incident, we have some sort of traffic patterns. For example, maybe like tens or hundreds connections coming into one receiver. And in this case, to do a reproduce of the incident, it will require a large deployment. We can use Lumina to kind of simulate this incident and to easily to investigate.
I see. We can take it offline, I think.
Yeah, sure.
Thank you.
Yeah, thank you.
So if
hello, thank you for the great talk, and I'm Jisoo from KAIST. So it was very interesting, but I think in this kind of middle box approach to test the behavior of the networking stack, it is very important to guarantee that your system does not trigger any additional behavior except for the exact one you intended. So does your system also have that kind of guaranteeing mechanism or verification method afterwards?
Yeah, sure. Very good question. I think it should be twofold. First, does our middle box or Lumina introduce extra latency or something to the traffic? To that end, we have empirical evaluation, and we find out that the actual overhead is very limited. And the other case is that we have this mirror trace, and we could verify if there is anything weird happened in the switch. Like if the switch is dropping packet, we can tell from the switch counters, the mirror trace counter, and the mirror trace pickup itself. Yeah, we have some modules in the code to verify.
Yeah, okay, thank you.
Great. So let's get all those, let's thank speaker again. And let's get all the speakers on the stage, and we will have a panel period. So offloading has been a very active research area. We've been navigating, even just for this session, network stack offloading, offloading memory disaggregation, packet processing applications, and we've been offloading to SmartNICs, programmable switches, sport VMs, and more, accelerators. And there have been performance optimization, and then debugging, multi-tenancy, lots of issues we have to consider. So any questions? It can be either on general or individual papers.
Teacher from Cornell, a question to all the authors here. I wonder, for the SmartNIC, what might be the right abstraction or semantics to those SmartNICs like exposed to the upper layer users? Let's say if today I like to just expose the P4 style pipeline-based abstractions to the SmartNICs, have you seen any special disadvantage or issue for doing so? Thank you.
Hi. Yes. So recently, the recent change is that people see there's some scenario like you need to program a SmartNIC to express some operations, something similar to the mesh action operation. That's why people are using P4 to program the SmartNICs in some cases. But there are other applications that are hard to express using the P4 language, like deep packet introspection, and and many other applications. So I think there's another trend, maybe future work, like people should work on is to design a better programming abstraction that can program both the ASIC cores, the fast pass, and the slow pass, like the ARM CPU cores. It could be a challenging task, but I do think that is necessary and for us to better to make it easy to offload applications to SmartNIC to achieve both flexibilities and high performance.
Other comments?
So a little bit of my thoughts is like it's similar to switches like SmartNIC or like generally NICs. We have like multiple vendors and we have like different interfaces. Like my vision, although I'm not working specifically in this direction, maybe hope is that we can have like general interfaces like Sonic for different switches. Underneath, we can have different vendors, and we can have different sort of devices, but we will have like general interfaces like Sonic or something like above this layer.
So I'm also like just starting with like offloading to the SmartNIC, and I feel like even with Xing, like one kind of SmartNIC depends on your application. There are several ways. So I'm doing a little bit about database and find that if you want to offload some of the database operators, there are several ways. Like you can do the ASIC stuff, you can also use the ARM cores, and there are also some like hardware accelerators in the SmartNIC, like there are different ways. And we're trying to also think about whether there's like a general or some general rules like where and what to offload.
Next question.
Jenny from Future Technologies. Maybe another way to look at the last question was maybe a little bit more forward-looking. So you guys have done a lot of SmartNICs and also programmable switches. So recently we started to get interest in this so-called like a decentralized data center architecture. What that means is basically move a lot of things from the CPU and even further make the CPU like an accessory of the SmartNICs, for example, or switches. I just wonder, how do you guys think in terms of making data center network as a new data center, this kind of architecture, could that be possible at all?
So to understand your question correctly, do you mean that do you want?
Sorry, maybe as an example. So recently, Microsoft has this project called Terminals, I think. Basically, SmartNICs is the center of the processing now, rather than the CPU itself. Just wonder what's your opinion on this kind of architecture?
I mean, there's a way to offload a bunch of things on SmartNICs, but I mean, from the perspective of performance, it does make sense. But there's also the question of like what kinds of applicability you have that you can offload. For example, on switches, there are certain types of applications such as telemetry that you can't really do elsewhere in the network. So yeah, it does make sense to have a unified approach that all the network users are able to consume. And one of the ways to do that is to be able to, as I'm trying to do as part of my work, is to be able to enable sharing of such devices, including SmartNICs, which have also been attempted in the past.
I can comment on that. So yeah, I think that's a good question, and I think it's a good time to rethink of the role of a programmable accelerator, including SmartNICs, FPGAs, programmable switches in the edge of disaggregated computing. So basically, when we have disaggregated setup, like the CPU mostly focusing on compute. Like we have disaggregated memory, disaggregated storage, but if you want to use this kind of architecture, you need to through the network to access them. Then that's where like you have this programmability, the flexibility to do more things. This is not just about performance. I feel like you can do more things such as security. Like you can enforce access control in the network now, but there could be more opportunity. I think yes, it could be an interesting direction like we can look at in the future.
Hi, this is Xing from Huawei Technology. I have a question about general question about the runtime probability. Because I think the operator has concerns about the stability of the network, right? Because the runtime probability always has concern, for the operators. I just wondering, in reality, how many operators deploy this kind of runtime, configuration technologies, programmability technologies?
So yeah, that's a great question. So, of course, enabling runtime programmability does come with the caveats. So one of the ways ways to approach this problem is delegation of liability to whoever is offloading functions. So if you use something like memory isolation or sandbox applications, then that is a way to constrain the effects of whatever is being offloaded onto the network to a subdomain of the network. So while it is indeed challenging to ensure that those offloads does not actually cause trouble to the rest of the network, being able to restrict the domain so that whatever is being offloaded only affects a part of the network would be a way to go.
Do you have any data like sorry?
Let's take the last question.
Maybe over here. Do I get to ask the last question of SIGCOMM this year? Oh, that is super cool. Yeah! I think this is my... I will try. That was my question. Super quickly, hey, I just wanted to commend you for super clear talks on interesting work. So to do that in the last session takes a lot, so congratulations. Just a quick comment, right? So it seems that SmartNICs, DPUs, IPUs, whatever we call them, these devices seem to be here to stay as a new computing device that seem to have two parts to them. One is a piece to process packets, a pipeline typically, between the line and the server. And then a set of cores on which are general purpose computing. And the packet processing pipeline, P4 or other languages that are designed for that seem to be a fairly good fit. For the general purpose cores, not really. Right, so general, C++, eBPF, whatever it is. And so there's this kind of split that's going on. And I see a lot of people scratching their heads who are trying to figure out how to use these devices that are trying to think about how to bring those two things together. Predictable performance pipeline, programmable set of cores. There's a missing piece here, which is a missing language or a way to combine what we have today that just it seems to be missing. And it's making it a lot harder, I think, for people who are trying to develop in this space. I'm not sure we have time to get everyone's thoughts on this. I wanted to put it out there as a missing piece, in case anyone else is interested in working on that, which I think would really ease the kind of work you're doing, as well as those who follow. And if any of you want to argue and say that I've just got that wrong, I'm happy to hear that too.
We don't need the answer. I think. That's yeah. Thanks for Nick for pointing out the. Thank you, Nick, for pointing out the interesting directions we can work on in the future. Yeah, and let's thank all the speakers again. That concludes the last session, and let's also thank our amazing chairs. Yeah, visual, any.